Edge AI applications have to balance intelligence with limits on power, memory, latency, and connectivity. That balance shapes every design choice in this chapter, from model size to deployment strategy. Design principles are the rules that help a product feel clear, usable, and consistent. The goal here is to understand the main idea behind those rules, because once that idea is solid, the details make much more sense. Edge AI design is where a working model becomes a real product decision. The main questions shift from technical possibility to fit, who it serves, where it runs, and what trade-offs it creates. A model can look valid on paper and still be the wrong choice once the setting, the users, and the risks are real. That is why design has to move beyond accuracy and into judgment about context. These pieces cannot be separated cleanly. A vague problem gives you a vague target. Weak data forces the architecture to compensate, and sensitive deployment settings make interface choices part of the technical design. A system can be technically feasible and still fail because people will not trust it, use it, or tolerate the friction it adds. Product success depends on both performance and whether the experience fits real human behavior. The wrist device idea works as an engineering concept, yet clashes with the moment-to-moment reality of lifting. When attention is on breathing and recovery, any extra input step becomes a burden, so the product competes with the activity it is supposed to support. A camera removes manual entry, so the workflow gets easier. At the same time, the sensing approach changes how people feel about the product, because convenience in one setting can become discomfort or distrust in another. Context decides the outcome. A camera may feel normal in a factory and invasive in a private room, so the deployment setting is part of the design, not an afterthought. The technical stack has to fit the environment, and the experience has to justify the stack. If connectivity is unreliable or human confirmation is hard to obtain, the architecture has to change rather than forcing the use case to adapt. Real deployment brings out the constraints that controlled testing misses: lighting, power, noise, habits, maintenance, and policy limits. Good design expects that gap and treats iteration as part of getting the assumptions right. The value of a design principle isn't the questions it sharpens. It pushes a team to ask whether the problem is right, who is affected, what success looks like in daily use, and which deployment conditions could break the obvious solution. A choice that helps one team can help thousands once the system is deployed widely. The same scale also multiplies mistakes, so responsibility has to be part of the original product definition, not a cleanup step later. The strongest practitioners do more than improve model metrics. They can see friction, context, and trade-offs early enough to explain why a product succeeds or fails, even when the technical result looks good. A design is ready only when it solves the right problem, fits the human experience, and stays acceptable in the real environment. If any one of those fails, the product still needs work. Design principles matter when separate technical choices turn into one deployment decision. The focus here is how problem framing, human factors, and operating conditions shape whether an edge AI product should exist at all and what form it should take. Those earlier topics stop being isolated once a team starts building a real system. The useful habit is to ask a single set of product questions. What problem matters? Who carries the burden? What limits exist? And what happens if the design is wrong? Accuracy alone does not make a system useful. A design can look strong in a lab and still fail because people will not set it up, will not trust it, or will be flooded with alerts that do not help them act. A practical design check starts with three questions that cut through the noise. Each one catches a different kind of failure, and a concept can break on any one of them. Problem fit asks whether the system is aimed at the right task. The model can be technically good and still miss the real operational need. So the question is always whether the output leads to a decision that matters. A classifier is only valuable if its answer changes something useful downstream, like replenishment, safety, or fewer missed events. In Riverwatch node, that means the local sensing has to support the real need, not just produce a label that looks impressive. Human fit asks whether the system works for the people who must live with it. Usability, workload, trust, and the cost of mistakes all matter, because a tool that constantly interrupts or confuses operators quickly loses its value. Freshline Inspector shows why this matters in practice. Even a working model can fail if it slows the line or forces constant manual interpretation. If operators have to babysit the system, the design has not really solved their problem. Context fit asks whether the design survives the real environment. Power, connectivity, latency, maintenance, and physical conditions all shape what is possible, and a prototype that works on a bench may collapse in the field. Battery limits, unreliable networks, harsh weather, and limited technician access can change the whole design. Scale matters too, because a small issue that is manageable at one site can become a repeating operational problem across many sites. These lenses work because each one can end the project on its own. A useful idea that frustrates users still fails, and a convenient interface that ignores field conditions fails just as easily. Architecture is not a neutral wrapper around the product. It defines what the product can become. If the use case needs local action, cloud-only processing is the wrong starting point. And if the hard cases need extra confidence, a single simple model may not be enough. Iteration becomes necessary because real data shifts, sensors behave differently outside the lab, and users react in ways a workshop cannot predict. Each prototype reveals a new constraint, and that feedback is part of the design process, not a failure planning. For a Riverwatch node, sending every local observation upstream may waste battery and bury the team in noise. A better pattern is restraint. Use local inference to suppress routine readings, then escalate only when confidence or severity crosses a meaningful threshold. The same test applies in industrial settings. If the inspection task is not worth automating, if operators do not trust the output, or if the system cannot keep pace with production, the architecture needs adjustment before deployment becomes expensive. Edge deployments are harder to patch after release, especially when one design gets copied across many sites. That is why misleading alerts, awkward workflows, or weak data practices are not minor issues. They can amplify across an entire operation. That judgment is exactly what product teams look for in practice. A strong candidate can explain why a technically solid model may still be the wrong deployment choice because of scope, architecture, or operational risk. A good edge AI design is not just a strong model. It is a model placed inside a workable product. These principles help a team make trade-offs deliberately before the architecture hardens and the cost of changing direction rises. Scoping edge AI starts with a feasibility question. What can be built now that is useful, testable, and honest about its limits? That mindset keeps the work grounded before the project turns into assumptions. The first pass should test whether the idea can work in the real world, not whether it sounds ambitious on paper. Feasibility gives the team a concrete target to validate before bigger commitments begin. That shift matters because early edge AI work is full of unknowns. Data quality, signal strength, and device performance all have to be proven under real conditions, and those limits can change the whole product idea. Estimation gets hard because the hidden work only appears after testing. Sparse data, noisy labels, and unstable environments can turn a seemingly simple feature into a much larger effort than expected. Model choice affects far more than accuracy. It can determine memory needs, power draw, latency, and even which hardware platform makes sense for the product. A small model may fit neatly on the device, while a larger one can force redesigns across the stack. That is why algorithm exploration often has to happen before the full deployment shape can be fixed. Locking the full system too early usually means building on assumptions instead of evidence. If the model needs more compute or misses response time targets, earlier design choices have to be revisited anyway. Most early failures come from a few ordinary problems, not mystery. Once those patterns are clear, it becomes easier to scope the first experiment correctly. A project may fail because the dataset is not representative, the signal is buried in noise, the hardware cannot keep up, or the performance target is simply too ambitious for that environment. Each of those problems changes what should be built first. Waterfall assumes requirements are stable enough to define once and hand off. Edge AI usually proves otherwise, because testing real data often reveals new limits late, when changing direction is already expensive. A narrow scope is not a smaller ambition. It is the practical way to reach a result that can be tested in the real world without betting the whole project on one unproven idea. The first release should not be a toy. It should isolate one slice of the problem that can be measured under realistic conditions and still tell the team something useful. For a factory inspector, one defect class is enough to begin if it is frequent, expensive, and detectable with reasonable confidence. Catching that one issue early can create real value before the system expands to harder cases. The same logic shows up in vehicles. Adaptive cruise control works because the operating envelope is limited, while full self-driving has far more road types, interactions, and edge cases to manage. Good scoping is really about learning quickly from reality. The first release should be narrow enough to build and measure, but meaningful enough that success matters. The goal is not to predict every outcome in advance. The goal is to pick a first version that reveals what the system can actually support and what users will actually value. Context changes the design. A stable factory floor is very different from a dusty yard, a moving vehicle, or a battery-powered sensor, and the scope has to respect those limits from start. Strong scoping creates practical value beyond the first build. It helps teams avoid dead ends and choose work that can actually ship. That skill matters across product design, machine learning, and systems planning because it turns ambition into something implementable. A good scope protects the team from expensive false starts. The deeper lesson is that Edge AI works best when the first release is deliberately limited and testable. Let evidence from that first version shape the hardware, software, and deployment path, then grow from there. The strongest teams do not promise everything at once. They prove one useful result in one real setting, and that gives them a solid base for the next step. Scoping an Edge AI solution is really about choosing what the system can realistically do, where it can do it, and what trade-offs come with that choice. The main issue is not just technical ambition. It is whether the idea can survive contact with hardware, data, and real deployment conditions. Uncertainty changes the way a project gets planned. The model, the sensor, the device, and the environment all depend on one another, so early decisions are rarely isolated. A change in one part of the system can force changes everywhere else. That is why the algorithm often has to be explored early, because memory, sensor input, speed, and power limits all shape what the final design can be. Conventional software usually starts from stable assumptions, but Edge AI often starts with unanswered questions about signal quality, dataset coverage, latency, and power use. Those uncertainties are not side issues. They decide whether the project moves forward at all. Broad commitments become dangerous when the common failure modes are still open. If the data are weak, the environment is noisy, or the device cannot support the model, a fixed plan will fail long before the product feels complete. The first useful boundary is the one that makes the problem feasible. Narrowing scope is not giving up. It is finding a version of the task that can actually work in the real setting. The best scope is the smallest one that still produces real value. Once that operating envelope is clear, the team can decide whether the system deserves to grow wider. That comparison shows why constraint matters. A narrow driving task can be useful because the assumptions are fewer and the environment is more controlled, while full autonomy has to survive a far larger set of edge cases. Edge AI often creates value through partial solutions that are trustworthy in a specific setting. A defect detector, a wake word model, or a small sensor fusion system can support real work even though none of them solve everything. Two examples make the idea concrete. One shows constraint as a design strength, and the other shows how to cut a large problem down to a testable first slice. Riverwatch Node works because it is tuned to a low-power field setting, not because it tries to replace a central analytics platform. Local sensing and selective reporting reduce energy use and bandwidth while keeping the system practical. Freshline Inspector shows the value of a smaller first release. A single inspection target lets the team learn from real production conditions before taking on full automation, and that learning can guide the next expansion. A minimum viable product in Edge AI is not just a smaller product. It is a test of the assumptions behind the design. It tells the team whether the signal, the model, the device, and the users all behave the way the plan expects. Deployment choices are tied together. So model design cannot be separated from hardware and sensing. The right model on paper may still be the wrong choice for the device that has to run it. A model may look fine in a lab and still be too large, too slow, or too power-hungry in the field. When that happens, the fix is usually to simplify the model, adjust the sensor input, move some processing upstream, or narrow the task until it fits. That is why incremental iteration matters so much. Real deployments show where the signal breaks, where the hardware overheats, where the data drift, and where people trust or reject the output, which gives the team a safer path forward. The scoping stage rewards fit more than size. A useful plan is the one that can actually be built, tested, and improved where the system will live. That does not lower the standard. It raises the quality bar by asking whether the project can survive the real environment instead of only sounding impressive on paper. Employers value this judgment because it turns promising ideas into feasible first releases. The person who can define the useful first slice often adds more value than the person who can imagine a huge system that never ships. That is the practical rule to keep in mind. Use scope reduction to buy clarity, then let evidence decide how far the system should grow. Design goals determine whether an edge AI idea becomes a real product or a dead end. The point is to define the outcome, the technical limits, and the release boundary before development hardens the wrong choices. A team can pick the wrong model and still recover. But if the goals are vague, the whole project drifts. Clear goals tell you what success looks like and what would be enough reason to stop early instead of sinking time into the wrong shape of system. A useful way to organize the problem is to separate goals by what they control. One layer is about the product outcome, one is about the machine behavior, and one is about whether deployment is acceptable at all. Systemic goals start with the real-world result the product should create. That means looking beyond model metrics and asking how people's work, decisions, or routines should change. These goals ask about the effect on the environment around the system. A good systemic goal talks about behavior change, reduced workload, or faster and safer decisions, because those are the outcomes a product is supposed to improve. A shelf detector can report high accuracy and still fail the product goal if staff do not get useful help. The stronger goal ties the model to the store workflow, so the alert arrives when it can actually speed up restocking work. Technical goals narrow the focus to how the AI component must behave. They turn the product idea into measurable limits on error, latency, memory, power, and robustness. These are the engineering thresholds that make a device workable. A model may be accurate in the lab, but if it is too slow, too large, or too fragile to survive real input, it is not technically ready. For keyword spotting, generic accuracy hides the failures users actually feel. False accepts create unwanted wake-ups, and false rejects make the device miss the command. So those rates are the numbers that really describe system behavior. Values-based goals set the moral boundary around the system. They define what harms are unacceptable, what uncertainty is too risky, and what oversight must exist before anyone can ship it. These questions are about responsibility, not just performance. A team needs to know which user groups must be protected, which failures cannot be tolerated, and what review process must happen before release. Medical systems make the stakes obvious because a wrong recommendation can do real damage. Even when the model looks strong, the team still needs clear gates that decide whether it is only assisting a clinician or crossing into territory that requires professional approval. These goal types must stay distinct. One describes why the product exists, one measures whether the mechanism works, and one decides whether deployment is acceptable under current conditions. That separation only works when the right people weigh in. Operators, customers, domain experts, and reviewers each see different risks, and their input keeps the thresholds realistic instead of optimistic on paper. Good goal setting starts with the baseline. If a manual process or a simple heuristic already works well enough, the real question is whether AI improves the outcome enough to justify extra cost and complexity. That matters especially in existing systems that already provide value. A rough rule can be cheaper, easier to explain, and good enough, so the AI has to earn its place by improving the operational result, not by looking sophisticated. Once the baseline is clear, the team can set the floor for usefulness. Minimum viable performance says when the system is worth continuing, and milestones give the project checkpoints, so progress is measured in stages rather than hoped for all at once. Go/no-go criteria prevent endless tuning when the system is not meeting the target. They give the team a pre-agreed point to stop, pivot, or narrow scope before the work turns into a sunk cost exercise. Release planning also needs metrics from the real deployment setting. Time saved, alerts acted on, missed events, battery life, and manual follow-up often say more about value than a clean test set score ever will. Edge systems live in changing conditions, so launch performance is not the end of the story. The goal-setting stage should already include how drift will be detected, who will respond, and how the system will be maintained over time. Clear goals simplify every later choice: data collection, architecture, hardware, failure priorities, and review decisions. They also separate someone who can train a model from someone who can scope a product, defend the thresholds, and support a responsible release. The sequence matters. Start with the outcome, the technical limits, and the release boundary, then compare against the current solution and set milestones and stop rules. If a design cannot satisfy that chain of reasoning, it is not ready to build. Design goals have to fit the real system, not just the model. The focus here is how to turn a technical idea into an application goal that improves outcomes in the field. A model can look excellent on paper and still solve the wrong problem. In shelf restocking, the useful target is not just spotting missing products. It is cutting the time shelves stay empty and making it easier for staff to act quickly. That shift matters because the job is to improve the world outside the model. A strong application goal names the change you want to see, such as faster response, fewer misses, less labor, or safer operation. The clean way to set goals is to begin with the result the organization actually wants. Once the outcome is clear, the technical work can be chosen to support it. Freshline Inspector should be framed around better line quality control, not around building a vision model for its own sake. That wording forces the team to think about early defect detection, less rework, and fewer false alarms before any architecture is chosen. A model can score well and still fail if alerts arrive too late or people do not trust them. The better choice may even be a smaller model, if it fits the device, the latency limit, the power budget, and the real workflow. A design goal only makes sense when compared with the current process. The baseline tells you whether AI is adding value or just adding complexity. If the current process already works well and cheaply, the AI layer may not be worth it. If the current process breaks in predictable ways, the baseline shows how large the gap is and what kind of improvement matters. That comparison is practical, not just evaluative. It tells the team whether the project deserves to exist, how far the target should reach, and where the main risk sits. Business goals have to become measurable constraints before engineering can succeed. The bridge between purpose and implementation is a set of technical targets tied to the real use case. Those targets might be latency, false alarm rate, missed event rate, battery use, local processing time, or sensor quality. They're the conditions that make the outcome possible. Smart home keyword spotting shows the point well. A device succeeds when it responds to the right phrase and ignores ordinary speech, TV audio, and background noise, so false accepts and false rejects matter more than a single accuracy score. Metrics should be considered before the system is built, not after the wrong path is fixed in place. Minimum viable performance means the lowest level that still justifies deployment under the real operating conditions. Some goals are about safety and trust, not just efficiency. Those cases need a hard release boundary that says when the system is not ready, even if the numbers look good. A system can meet technical targets and still fail a responsible launch if the consequences of error are too serious. That is why release decisions sometimes depend on values as much as on performance. Medical diagnostics makes the issue unavoidable. A useful system may need human review, advisory-only outputs, or strict limits on uncertainty because the cost of error is so high. Those thresholds also tell the team when to stop and change direction. If the safety bar cannot be met, the right response may be to narrow the task, add oversight, or walk away from the use case. The size of the problem is part of the design. Clear goals help decide what the system should do, what it should not do, and what should be left out for now. That narrowing is not a compromise. It is often the smartest strategy. Edge AI projects fail when they promise too much and succeed when they define one bounded task well. Adaptive cruise control is a contained problem, while full autonomy asks the system to handle a much wider world. Sometimes the cleaner solution is a rule, a workflow change, a better sensor placement, or a human check instead of a larger model. That ability is a professional skill. When goals are measurable and deployment-aware, product, hardware, data, and domain teams can work from the same target instead of arguing past one another. A useful design can answer a short set of checks before development starts. Those questions force the team to prove that the goal is real, measurable, and worth building. The team should be able to name the outcome, the baseline, the right metrics, the minimum acceptable performance, and the conditions that make the system unsafe. If AI is not the best option, the simpler alternative should be clear too. Clear answers mean the project has a defensible target rather than a vague model idea. Without that clarity, implementation is usually premature. The guiding rule is that Edge AI starts with the application and works backward from there. Model choice matters, but only after success has been defined in the real context. Those three pieces give a practical way to break an Edge AI system apart. The goal is to decide where each responsibility belongs so the design can actually be built, deployed, and maintained. That lens keeps the architecture grounded in real responsibilities instead of vague ideas. It helps separate what the device must do locally from what can live elsewhere. A good design starts with boundaries, not model choice. Once the goal is clear, the important question becomes which parts belong on the device, which belong in the code, and which belong in an outside service. That simple split gives a working map of the system. It is not the whole story, but it is enough to start placing functions in the right place. Hardware is the physical device, software is the code running on it, and services are the outside systems it depends on. Keeping those three roles separate makes trade-offs much easier to see. The point is not classification for its own sake. The point is to ask where each function should live so the system matches its constraints. Now the split becomes concrete. Each layer has a different job, and that job changes what the system can do reliably. Hardware sets the ceiling for local performance. Processors, memory, sensors, power, and connectivity all constrain what the device can sense, compute, and communicate on its own. Software gives the device purpose. Drivers, pre-processing, inference, and application logic turn raw input into a decision or an action. Services handle the work that is too heavy, too centralized, or too operationally complex for the edge device alone. They might store events, manage fleets, or provide remote analytics and coordination. That division is never fixed. The right balance depends on the environment, the deployment, and the limits of the platform. A lab device, a factory system, and a remote field unit can solve similar problems while using very different boundaries. The context decides what can stay local and what needs outside support. When connectivity is intermittent, the device has to carry more of a load itself. Sampling, filtering, local detection, buffering, and selective reporting become part of the edge design instead of relying on a remote service. A weak network does more than slow communication. It changes the architecture by forcing the device to be self-sufficient and by shrinking the role of off-device features that cannot be trusted day to day. A production site often supports a different split. Local software can handle immediate inspection, while services can collect results, track trends, sync thresholds, and support monitoring across the fleet. The important decision is not whether the cloud exists, but which functions belong where under real constraints. Architecture should follow the platform, the network, and the job the system must perform. Existing hardware can be the main limitation. If the platform is fixed, efficient code, model compression, staged inference, and narrow feature scope may matter more than trying to change the device. Other problems need more capacity than a small device can provide. Large models and centralized analytics can make services the better fit, not because they are fashionable, but because the task demands resources and coordination. That leads to a system made of multiple kinds of compute. One part senses, another does first-pass inference, and a service handles heavier analysis or storage. So each component does the work it is best suited for. That skill matters because teams need someone who can turn deployment limits into architecture decisions. The job is to place each function on device, in software, or in a service, and to leave out anything the platform cannot support. Once those boundaries are clear, the next design step becomes easier to justify. The system can now move toward an architecture pattern that fits the hardware, software, and services instead of fighting them. Edge AI architecture depends on how work is split across the device, the software, and outside services. That split determines what the system can do in the real world, not just in a diagram. The same problem can be built many different ways depending on what stays on the device, what the software handles, and what gets pushed to services. That matters because an edge system is an arrangement of capabilities and constraints, not just a model running somewhere. Hardware sets the physical limits of the design. The device's processor, memory, sensors, power, and connectivity determine what kind of edge behavior is even possible. A battery-powered sensor node, a rugged industrial camera, and a mains-powered gateway all create different design conditions. Those differences shape latency, reliability, and how much intelligence the device can carry on its own. A weak connection or a scarce power budget changes the whole strategy. The device may need to decide quickly, use less energy, and avoid depending on constant back and forth with a remote system. Software turns the hardware into a working system. It moves data in, shapes it, runs inference, and decides what action should follow. Drivers bring sensor data into the system. Signal processing prepares it. Inference produces a prediction or alert, and application logic decides what to do with that result. Each layer has a different job, and the combination is what gives the hardware purpose. Even a constrained device can do useful work when the software is carefully designed. Smaller models, feature extraction, stage processing, and good thresholds often get much farther than trying to copy a large cloud setup onto a small device. Services extend the edge system beyond the box. They handle the external functions that the device depends on, such as storage, updates, coordination, and heavier analysis. Those services may synchronize data, manage fleets of devices, archive events, or run tasks that are too large for the local hardware. They're not on the device, but they still belong to the application architecture. A bigger model, long-term history, shared context, or centralized control can justify pulling services into the design. That choice is about fit, not superiority. Some tasks simply go beyond what the device can handle alone. A small sensing node makes the split easier to see. In a low connectivity setting, the design has to favor local processing and careful reporting instead of relying on constant remote access. Imagine a deployed sensor with a tight power budget and an unreliable link. In that environment, waiting for every reading to travel to a remote service would make the system fragile and slow. A better approach is to filter and interpret readings on the device, then send only the events or summaries that matter. That keeps the system useful even when the network drops, and it shows how architecture has to follow operating conditions. A factory deployment pushes the balance in a different direction. The device may still inspect locally, but the surrounding system often needs extra coordination and record keeping. On a production line, the edge device may be only one piece of a larger stack. Quality data, monitoring, exception handling, and integration with production systems can all depend on services around it. A narrow inspection task may fit on a single device, while broader factory needs justify more infrastructure. The architecture grows because the job demands it, and that is the real design discipline. The main design question is how to balance performance, resilience, and operational cost. Every decision about where to place computation changes what the system gains and what it gives up. Pushing work onto the device can improve responsiveness, privacy, and independence, but can also raise power use and software complexity. Leaning on services can add capability and coordination, but it also increases latency and dependence on connectivity. A thermostat, a remote sensor, and an industrial camera do not impose the same constraints. The useful skill is turning business needs and field conditions into a system that can actually run where it is deployed. That boundary is the starting point for the architecture. Once the responsibilities are clear, the rest of the design becomes a matter of choosing the pattern that matches them. Edge AI architecture starts with a simple question. What is the smallest system that still meets the job? The rest of this lesson is about choosing the right loop, adding complexity only when a use case truly needs it. A good design begins with the least complex setup that still satisfies the real constraints. That keeps energy use, latency, memory, and maintenance under control from the start. The practical decision is not how elaborate the system could become. It is whether a simpler architecture already solves the problem within the limits of power, delay, memory, and support effort. Riverwatch Node shows that idea well. It needs to stay cheap to run, detect only meaningful events, and avoid unnecessary processing. Freshline Inspector may justify more structure because production lines create different demands, but the design choice still comes from the workload, not from a desire to be more advanced. At the center of every edge system is a repeating loop: sense, infer, decide, act. Once that loop is clear, the rest of the architecture becomes easier to place. A camera, sensor, or gateway collects input, the model interprets it, and the device responds. The main architectural question is where that cycle runs, how often it repeats, and where each decision boundary belongs. The model never works alone. Firmware, operating system services, hardware APIs, and peripherals all shape what can actually be sensed, computed, and controlled, so the design has to fit that stack instead of ignoring it. The usual starting point is one loop, one model, and one decision path that give you a clean baseline before any extra structure is introduced. A security camera is a good example. Capture the scene, classify the person, trigger an alert if needed. Many useful products work well with that simple pattern, as long as the threshold and response are chosen carefully. Riverwatch Node benefits from that same discipline. If a basic local inference loop already meets the energy, latency, and reliability targets. Adding more machinery only makes the system harder to run and maintain. Sometimes one prediction is not enough, and the architecture has to split work across multiple models or stages. That is where more specialized patterns become useful. Extra structure is worth paying for only when the task asks for more than a single answer can provide. That keeps complexity tied to a real requirement. An ensemble uses several models to make the same kind of prediction and then combines the results. The benefit is stability. Individual weaknesses tend to cancel out, so the final decision is often more reliable than one model alone. A parallel flow runs different models side by side for different purposes. One model can make the main classification, while another watches for unusual input and acts as a guardrail when the signal looks suspicious or incomplete. A series flow passes the result of one model into another. That helps when the second model can work better on a simpler representation, like using pose estimation first and a posture classifier second. A cascade is a cost-saving design. The whole point is to protect latency and energy. When the early stage filters out most cases, the heavy computation runs far less often, which makes the device much more efficient overall. A battery-powered keyword device is the classic case. A tiny always-on detector watches continuously, and only a likely wake word wakes the larger model, so the most expensive inference happens rarely. Cascades can grow into multiple layers, each adding a finer check or even a better data source. That makes sense when earlier stages are cheap and later stages are reserved for cases that justify the extra cost. Some problems are not solved by one signal or one style of logic. Fusion and hybrid decisioning combine inputs or combine methods, so the system can judge the situation more completely. When several sensors tell different parts of the story, the combined view is stronger than any single reading. A wearable measuring heart rate, temperature, and motion can make a better judgment because the signals support one another. Hybrid systems split responsibility between deterministic rules and machine learning. That works well when some cases are clear, policy-driven, or safety-sensitive, while the ambiguous edge cases need model-based inference and a clearer audit trail. The right architecture comes from the task, the hardware, the data, and the risk, not from which pattern sounds most impressive. The job is to fit the design to the real constraints. A simple pipeline may be enough, while an ensemble, cascade, parallel flow, series flow, fusion, or hybrid design may be better for a specific constraint. Each pattern solves a different kind of problem, so the choice should follow the operational need. That judgment is what strong edge and embedded engineers are expected to make. In a design review, a good answer explains why one architecture is easier to power, trust, and maintain than the alternatives. The core mental map is straightforward. Begin with the smallest workable loop, then choose sequence, parallelism, cascades, fusion, or hybrid logic only when the use case truly calls for them. That keeps the design grounded before implementation begins. Application architecture on the edge is about how sensing, inference, and action fit together under real device limits. The shapes of those flows matter because they determine whether a system stays simple, responsive, and practical. The first useful pattern is the application loop, where a device senses, interprets, decides, and acts in a repeating cycle. Once that loop is clear, the rest of the architecture patterns become easier to read. That cycle is the core of many edge systems. A device does not just produce one prediction and stop. It keeps reacting to changing conditions while staying inside power, latency, and memory constraints. Riverwatch Node makes the loop easy to see in practice. Most readings should pass quietly, but a meaningful change should trigger a report, and that output then shapes the next cycle of behavior. Those layers are what turn the idea into a device that actually works. Firmware starts sensors and manages power. The operating system coordinates shared resources, and hardware APIs expose the chips and peripherals so the same application logic can move across platforms. Once the loop is clear, the next step is choosing the right architecture for the job. Different problem types call for different flows, and the visual pattern often tells you what trade-off the system is making. The simplest design is still the most useful when it fits the task. One input, one model, one decision is often enough for a camera or sensor system, especially when latency and energy budgets are tight. An ensemble is about agreement among models that aim at the same answer, while parallel paths split the same input into different jobs. That lets one branch classify and another watch for anomalies, so the system can make two kinds of decisions from one signal. A series architecture stages the reasoning. The first model transforms the raw signal, and the second model uses that transformed result to make a higher-level judgment, which is useful when the original data is too messy for a direct answer. A cascade adds a cost strategy to that stage flow. A small always-on detector handles the easy cases, and only uncertain or interesting events go to a heavier model, which saves battery and reduces unnecessary work. Fusion is different because the advantage comes from more evidence, not more models. When motion, heart rate, or another context signal are combined, the decision becomes more robust against noise, missing data, or ambiguity. The real skill is matching the architecture to the problem, not collecting clever diagrams. Good design starts with the constraints and works backward to the simplest flow that can still meet them reliably. A team can always add complexity, but complexity only helps when the product genuinely needs it. The better question is what the system must do, how fast it must do it, and how much power or risk it can tolerate. Each shape tells you something different about the design. Agreement, split functions, staged interpretation, conditional compute, and multi-signal evidence are 5 distinct ways to organize an edge application. Those examples make the trade-offs concrete. A camera may only need a single pipeline, a wakeware device often needs a cascade, and Riverwatch node should stay quiet until the reading becomes actionable. Not every decision should come from a model. Rules are useful when some cases need fixed handling, clear thresholds, or a safety override that a learned model should not be trusted to decide alone. A practical system often combines thresholding, learned inference, and rule-based overrides. That mix handles the easy cases deterministically, lets ML manage the messy middle, and protects the product when policy or safety matters more than prediction. That ability to sketch a sensible flow is a real engineering skill. It shows that you can justify the design, defend the trade-offs, and move from an idea to a system that can actually be reviewed and built. A strong design process starts with a loop and then narrows to the pattern that fits the device, the data, and the operational risk. If the job is simple, keep it simple. If the job needs multiple signals or stage decisions, shape the flow to match that need. The final check is whether the architecture can be justified as the simplest viable edge AI flow. If it can, the design is ready for feasibility review. If it cannot, the system is probably carrying unnecessary complexity. A good sketch should answer that question clearly. When the answer is yes, the architecture has a real chance of surviving constraints. And when the answer is no, the flow needs to be simplified before anything else is added. Complex edge AI systems are usually built by combining familiar pieces in a careful order. The important question is not whether each piece is clever, but where each one belongs and what happens when one of them is slow, uncertain, or unavailable. An edge architecture often looks like a chain of ordinary parts working together. What matters is fit. Each stage should handle the job it is best at, and the system should still behave sensibly when a stage cannot do its part. That pattern saves energy because the low-power device handles the routine case and stays quiet most of the time. The stronger processor only wakes up for the harder cases, so you get faster response without paying the full cost on every input. A cascade becomes more useful when the stages are split across devices. One device can make a quick local judgment, and another can take over only when the first device decides the situation needs more context or more compute. A smart sensor can act as a gatekeeper instead of trying to solve the whole problem itself. If the reading looks suspicious, the gateway can combine more signals, run a deeper analysis, and decide whether to escalate the event farther. That same idea often reaches the cloud in a two-stage design. A tiny local model catches the likely trigger first, and the cloud only steps in for confirmation when the edge device has done enough to justify the extra cost and data movement. Riverwatch Node and Freshline Inspector follow that same logic in different settings. The first stage is meant to be economical. The second stage is meant to be stronger, and the whole structure should match how often hard cases really appear in the field. Sometimes the best decision point sits between the smallest devices and the cloud. That middle layer can see enough context to make a better choice than any single sensor, while still staying close enough to the edge to keep the system responsive. A single vibration reading may mean very little on its own. When a gateway combines vibration, temperature, current draw, and timing, it can recognize a pattern that none of the sensors could justify alone. That middle layer reduces unnecessary traffic and still gives you a richer view of the system. It is a good choice when the devices are small and constrained, but the decision needs more context than any one node can provide. High-risk systems need more than automation. The design has to say clearly whether a person is part of the decision, watching the decision, or reviewing afterward. Those three oversight modes sit at different points on the control spectrum. Each one changes who makes the final call, how fast the system can act, and how much trust you need in the machine output. With human-in-the-loop design, the model can suggest an answer, but the person still owns the decision. That fits situations like medical support, where judgment, context, and consequences all matter at once. Human on the loop gives the machine more freedom, but it also depends on careful monitoring. If people are only needed occasionally, attention can drift and the oversight becomes weaker than it looks on paper. Human audited operation is different again. The system can move quickly, but its actions are recorded and reviewed so that policy violations or mistakes can be corrected after the fact. That matters even when physical safety is not the issue. In policy or sports settings, a biased system can still cause unfair treatment. So oversight has to protect equity and legitimacy as part of the architecture. A production system also needs a plan for when the model path cannot be used. The design should still behave sensibly if the model is disabled, untrusted, or simply the wrong tool for a particular input. Graceful degradation means the application does not collapse when the ML part fails. It falls back to a safe, sensible behavior instead of treating the model as the only possible route through the system. A deny list or bypass rule gives you a clean way to express that idea. Certain inputs, modes, or conditions should route straight to non-ML handling, and that decision should be controlled by configuration, not guesswork. The first branch catches the cases that should never reach the model, and the second branch handles the rest. The important idea is not the syntax, it is the explicit choice to route some inputs away from ML on purpose. A real deployment needs that escape hatch ready in advance. If remote updates are possible, the bypass rules can change without a redeploy. If not, there still needs to be a local way to change behavior when conditions demand it. Freshline Inspector makes the pattern concrete. Routine items can stay automated, but unusual products, weak sensor feeds, or model drift should push the system in a manual review instead of forcing a bad automated answer. The strongest design is not always the most layered one. A thermostat may only need a simple local flow, while a medical, industrial, or vehicle-related system may justify more stages because the risk and complexity are much higher. That is the real job of architecture work at the edge. The structure has to tell the system when to stay local, when to escalate, when to involve a person, and when to step around ML entirely. Architectures become real when the control flow is written down in code. The focus here is how design patterns decide when ML runs, when a cheaper rule is enough, when a case escalates, and when the system stops and waits for a person. A pattern only matters if the application can enforce it at runtime. In edge systems, every branch needs to be visible so the software can choose local processing, escalation, or refusal instead of behaving like a vague black box. Conditional routing is the core idea behind cascades. The system tests an input, compares the result with a rule or threshold, and then sends it down the right path. That makes the architecture practical. Routine cases can be handled by cheap checks, while expensive inference is reserved for inputs that are uncertain, risky, or unusual. Explicit control flow tells you exactly which cases stay local, which ones get promoted, and which ones are bypassed. That visibility is what lets the system save latency and bandwidth while keeping sensitive data on the device when possible. A production line makes the pattern easy to picture. Clear cases stay with the lightweight local stage, but ambiguous samples trigger a second inspection layer on a gateway, nearby computer, or cloud service when the extra context is worth it. A small dispatch routine is enough to show the architecture in code. The point is to make the decision path executable, not to build a full product. The example matters because it turns the design into behavior. Once the branching is coded, the team can see exactly how samples move through local checks, escalation, human review, and fallback handling. The first part defines a decision record, so every outcome carries a label, a confidence score, and the route it took. The inspection system then wires together four behaviors: a local check, a stronger check, a human queue, and a fallback path. The inspect method makes the policy explicit: bypass ML for denied samples or disabled service, accept high-confidence local results, send very uncertain cases straight to review, escalate borderline cases to a stronger model, and hold anything still ambiguous for a person. That structure is the architecture in miniature. The deny list and the ML switch let the team bypass model inference for bad cases, maintenance windows, compliance limits, or model retirement. So the system still has a defined path when the model cannot be used. Escalation should be deliberate. A local stage can wake a gateway, call the cloud, or hand work to another processor only when the available context is no longer enough. That keeps the higher cost layer narrow and useful. A sensor or audio pipeline can stay quiet most of the time, then pass on only the cases that cross a threshold or look unusual, which save power and bandwidth. Different devices need different stopping points. A thermostat may stay local, while a safety monitor or sensor fusion system may need a gateway or cloud stage because the decision depends on more context or heavier compute than the device can provide. Human-in-the-loop design changes what the software is allowed to do. The system may compute a result, but it should not act on it until a person has approved or cleared the case. That means the implementation needs review states, queues, and manual checkpoints. The action is blocked until the person confirms it, which is very different from a system that auto-acts on every prediction. Safety-sensitive workflows depend on that pause. When the risk is high, the code should allow exception paths and overrides so the system can stop instead of forcing a guess. A production system cannot assume the model is always present or always allowed to run. The fallback path has to be part of the architecture from the start, not added after failures appear. Fallback can take different forms depending on a risk. The system might use deterministic rules, choose a conservative default, or alert an operator and suspend action until service returns. For Freshline Inspector, the basic rule path can still separate clear pass and clear fail cases while ambiguous ones wait for review. If the ML component is down, the line still stays safe and operational instead of stopping without a plan. This is where architecture becomes a hiring signal. Teams want engineers who can show what happens when confidence drops, hardware changes, connectivity disappears, or safety rules override automation. Strong production work needs code that reflects the system design. Clear escalation logic, dependable fallback behavior, and a clean split between local, gateway, and cloud responsibilities matter more than a model demo that only works under ideal conditions. That is especially true in embedded, industrial, and consumer edge roles, where maintainability and control matter as much as model quality. Good code can be audited, updated, and shut down cleanly, so the architecture is not separate from the implementation. It is the implementation. A solid edge system makes its boundaries visible: stage boundaries, escalation rules, human review paths, and fallback behavior. When those choices are missing from the code, the system is usually optimized for a slide deck, not for the field. Design patterns become useful when an edge AI idea has to survive real constraints. The goal here is to judge fit. The problem, the data, the hardware, and the deployment setting all have to line up. A pattern can look clean on paper and still fail in practice if the device is too weak, the data is unreliable, or the system is placed in the wrong environment. Good engineering starts with what the product can actually support. That approach keeps teams from overbuilding too early. Patterns are guidance. So the first version should solve the problem with the least machinery that still works, then grow only if a real constraint demands it. A simple first workflow makes the decision process repeatable. The point is to examine the real situation first, then choose the smallest design that can honestly handle it. The decision process moves in steps, and each step reduces guesswork. You're not locking in an architecture immediately. You're testing whether the fit is real. First, work from the data that exists. Then pick the simplest viable pattern. Write down why you chose it, test it against the deployment setting, and only move to a more complex option if a real limitation appears. That order matters because the same model can behave well in one environment and fail in another. Representative data and clear limits protect you from designing for the wrong conditions and help others use the system safely later. A thermostat is a good example of context-shaping architecture. A single open room may work with one local device, while a multi-room home can justify a gateway setup with distributed sensors and a central hub, because the layout changes the control problem. A simpler pattern is usually the safer default when it meets the need. More parts mean more cost, more latency, more maintenance, and more ways for the system to fail. So added complexity needs a clear reason. The same logic applies when choosing a model. The right algorithm depends on what the scene looks like because object size, spacing, and visibility change how well a method will work. In a farm counting system, one detector may work better when animals are larger and easier to separate, while another may suit a more spread out scene. The important point is that model performance shifts with the visual conditions, not with the name of the method alone. A model that looks strong in a controlled test can still be a poor field choice if the animals are small, far apart, or partly hidden. Good selection ties dataset understanding to the deployment context at the same time. Bias shows up in more than the dataset. Product choices, algorithm choices, and deployment choices all tilt the system towards some outcomes and away from others. That means bias is built into the design process itself. What the system is for, how the model learns, and where it is used all shape its behavior. Product bias appears when the system bakes in assumptions about the job it should do. A small apartment thermostat and a multi-zone house thermostat are solving different problems, so their success criteria are different too. Algorithm bias comes from a model and how it was trained. One detector may favor large, separated objects, while another handles clustered scenes differently, so the chosen method decides which features get attention. Deployment bias is the mismatch between the original design and the real place where the system runs. That is why validation against the actual environment matters. A sound design in one setting can become unreliable in another. Good teams write down the reasoning before implementation starts. That record makes assumptions visible, so the architecture can be reviewed instead of just accepted. A simple diagram shows the flow, and a short note explains why this pattern was chosen, what alternatives were rejected, and what would force a redesign. That gives everyone a shared reference for the decision. That documentation helps in two ways. It tells users and engineers what the system can and cannot do, and it gives the team a way to ask which assumption failed if the prototype misses the mark. For a medical device, the deployment setting can change the meaning of the whole design. A model built for one patient population or sensor setup may not be safe in another, so careful validation is essential when harm is possible. Some applications are too easy to misuse responsibly. When a foreseeable harm is severe, the design decision itself has to be questioned, and the safest answer may be strict limits or no release at all. That concern becomes even sharper when a system could be repurposed to identify targets or improve autonomous harm. In that case, disclosure and release decisions have to account for the risk of misuse, not just the technical performance of the model. This kind of judgment is one reason experienced engineers stand out. Being able to justify a simpler architecture, explain the trade-offs, and revise the plan when evidence changes matters a great deal in safety-sensitive work. That habit keeps design grounded in reality. Begin with the simplest pattern, align it to the deployment setting, write down why it makes sense, and treat any mismatch as a risk to solve early. Design patterns matter when an idea has to survive contact with real constraints. The focus here is how to choose, adapt, and justify a pattern based on the actual problem, not on abstract elegance. A good first design is the one that can meet the need with the fewest moving parts. From there, the architecture earns extra complexity only when the device, data, or environment makes it necessary. The goal is not to invent the fanciest system, but to make a useful one real. That starts by asking which pattern works if the assumptions hold, and only adding structure when the constraints demand it. If you jump straight to a cascade, gateway, or human-in-the-loop setup, you may solve problems that do not exist yet. A lean local design is often the right starting point when latency, unreliable networking, or on-device inference are the real pressures. Low-power systems need the same discipline because battery life and memory budget punish unnecessary layers. The right pattern depends on what the field conditions actually require, not on what seems architecturally complete on paper. A pattern gives structure, but it does not settle the design. The real work begins when you test that structure against data, device limits, and the way the system will be used. Pattern selection has to be iterative because the world pushes back. A team tries a candidate design, compares it with evidence and constraints, records the trade-offs, and then adjusts the fit. A thermostat-like product may work well with a single device pattern when the task is narrow and latency matters. When coordination, shared state, or heavier computation enters the picture, a gateway arrangement may fit better because the deployment context has changed. Factory conditions add timing, lighting, maintenance, and false alarm costs that a lab never captures fully. A pattern that looks fine in testing can become a liability if it does not survive those realities on the line. Good fit only appears when model behavior, system limits, and real usage all point in the same direction. If any one of those is ignored, the design can look reasonable and still fail in deployment. Mismatches usually show up in a few predictable ways. It helps to name them early, because each one points to a different kind of design risk. Product bias comes from hidden assumptions in the product idea itself. A system built for a controlled environment may depend on stable placement or careful upkeep, and those assumptions can break as soon as the product moves into a different setting. Algorithm bias is about match quality between the model family and the evidence it sees. Small objects, crowded scenes, motion, and occlusion all favor different inductive biases, so the best algorithm is the one that fits the real visual pattern of the task. Deployment bias appears when the operating environment drifts away from training assumptions. Representative data helps, but the harder question is still the same. What should the system do in the place where we'll actually live? Good design work should be written down before the choice is hardened into code. Diagrams and short notes keep the assumptions, trade-offs, and rejected options visible while there is still time to change them. The documentation should answer four direct questions: what problem the pattern solves, what it depends on, what it gives up, and what other options were ruled out. That record makes the design understandable to the whole team. This is more than paperwork, because a diagram or pros and cons list can reveal hidden dependencies before they cause trouble. A system described as local-only may quietly rely on network access, and a gateway may solve compute limits while introducing a new failure point. That habit matters in real engineering work because teams need people who can defend an architecture choice and state its cost clearly. The ability to justify a simple pattern and to say what would force a more complex one is a strong sign of judgment. Context is not background information. It is part of the design problem. Power, latency, privacy, reliability, and coordination needs all shape where logic should live and how the system should be organized. A thermostat forces a placement decision because control can happen locally or partly through a gateway. The right balance depends on latency, power, reliability, privacy, and how much coordination the product needs. An agricultural object detection system faces light, dust, weather, distance, and motion that can reshape the whole solution. A model that works on close, clean images may be the wrong fit for cluttered field scenes, so the deployment setting has to be part of the problem definition. Restraint is part of responsible design. When a system is narrow, unstable across environments, or likely to cause harm if misunderstood, the right move may be to narrow the scope, add oversight, or step back from the application entirely. Transparency about limits matters because a system can be repurposed in ways the original team never intended. If accuracy shifts with the environment or the use case is high risk, those limits need to be stated plainly. Restraint is not a lack of confidence. It shows that the team understands when a system is ready, when it needs more controls, and when the honest answer is not to proceed. The practical habit is to start small, adjust as the evidence becomes clearer, and keep the trade-offs visible while you do it. In Edge AI, the best architecture is the one that can withstand a real environment, not the one that only looks impressive at design time. Early design only becomes real when it leaves behind artifacts other people can inspect, question, and approve. The point of this part is to show how those deliverables turn a loose idea into a project the team can actually commit to. A good idea alone does not protect a team from bad assumptions. Shared documents create something concrete that can be checked before time and budget are spent on implementation. Edge AI forces several judgments at once. The team has to test usefulness, data readiness, deployment limits, and practical behavior together, because a weakness in any one of them can sink the whole plan. Before code starts, the team needs a packet that a reviewer can read in one pass. That packet should collect the main decisions so the project can be challenged while changes are still cheap. The first piece frames the problem clearly and gives a first pass at how the team expects to solve it. That keeps the project anchored to a real need instead of a vague idea. Scope has to be narrow enough to test. A minimum viable scope tells the team what belongs in the first version and, just as important, what stays out. Feasibility asks whether the idea can survive contact with reality. A short summary captures the main evidence for or against moving forward. Goals define success, standards define the target quality, and constraints define the boundaries the design cannot cross. Those three together keep the team from drifting. A flow sketch shows how the system behaves from input to action. It helps everyone see the sequence of events instead of arguing only about isolated features. The hardware sketch makes the physical setup visible. It shows where computation, sensing, and communication will live, which matters a lot at the edge. The software sketch describes how the logic is divided up. It clarifies pre-processing, inference, logging, alerts, and any human handoff. A design is incomplete if nobody knows how it will be kept alive. Support notes assign responsibility for updates, failures, and ongoing care. A checklist or gate turns the packet into a decision point. It gives the team a clear moment to approve, revise, or stop before development begins. Those formats can change from one chapter or team to another, but the purpose does not change. The work has to be visible enough for people to critique it before anyone starts building. A useful way to organize the early packet is to separate it into 3 clusters. That split keeps each document focused on a different decision the team has to make. The first cluster frames the problem, the second tests whether the idea should exist at all, and the third turns the chosen direction into something buildable. Keeping them separate makes the review much sharper. Problem notes answer who has the issue, why it matters, and what the first version might be. They stop the team from building around a wish that has never been made precise. Feasibility is broader than technical capability. The team has to ask whether the application is appropriate, worth the cost, supported by good data, and realistically deployable in the intended environment. Once the team decides the idea is worth pursuing, the design documents become the bridge to implementation. They spell out behavior, dependencies, operating conditions, and where each part of the system will live. These documents solve different problems, so combining them into one loose plan causes confusion. A review works best when each artifact has a clear job and a clear boundary. Freshline Inspector shows how those categories work in a real project. The same deliverables appear again, but now they guide a concrete inspection system instead of a general idea. The starting problem is practical and specific. Catch more defects without hurting throughput. From there, the team can compare narrow MVP options instead of jumping straight to full automation. At this stage, restraint matters more than ambition. A limited first release gives the team a chance to test the idea in the real environment without promising more than the system can safely deliver. The feasibility review then checks risk from several angles: safety and compliance, cost and operational value, data quality and representativeness, and the physical limits of cameras, latency, and inference all have to line up. Only after those checks do the design documents carry real weight. They describe the path through the system, the split between device and remote services, the software responsibilities, and a support plan that keeps the system usable after launch. That packet gives reviewers something solid to judge. It can be approved, revised, or rejected before the team spends time building the wrong thing. A low-power field system changes the constraints, not the logic of design work. The documents still have to clarify the need, test viability, and describe how the system will operate. Riverwatch Node has different goals and different limits, but it needs the same basic artifact structure. The team still has to make the idea legible before it can be trusted in deployment. Battery life, weather exposure, and patchy connectivity make ambiguity expensive. When the field environment is constrained, good documents prevent costly guesswork later. These artifacts should be treated as working inputs, not permanent truth. As measurements and field evidence come in, the documents need to move with them. A feasibility note may change after sample data reveals bias. A hardware sketch may change after power tests. A support plan may change once the team learns what remote updates really cost. That ability to revise is the point. Writing the documents is not about freezing the project. It is about making the project clear enough to improve. Design review is the moment to test whether the path is credible and whether the remaining risk is acceptable. If the packet exposes a weak idea, the right response may be to narrow, redesign, or stop before the build begins. The ability to turn an AI idea into reviewable artifacts is a practical career skill. It is often what separates a promising sketch from a system that actually gets shipped. Teams need people who can work across model quality, hardware limits, deployment reality, and operational responsibility. In Edge AI, that combination of judgment is often what gets a concept over the line. The practical checkpoint is simple. Build the documents first, then use them to prove the idea is worth pursuing and the risks are manageable. Once that packet is coherent and reviewed, implementation starts from a much stronger base. Edge AI work becomes real when it produces reviewable artifacts that let others test the idea, refine it, and judge whether it deserves engineering time. A sketch or a good conversation is not enough. The packet gives other people something concrete to challenge, revise, and use when deciding whether the project should move forward. The documents capture the problem, the candidate solution, the feasibility checks, the goals, the architecture, the constraints, and the rule for proceeding. That record becomes the handoff from speculation to a build-ready plan. The early packet is easier to manage when those deliverables are grouped into three parts: problem and solution notes, feasibility studies, and design and planning documents. That structure keeps the work orderly. First, the team frames the problem, then it tests whether the idea can work, and then it records the design in a form that others can implement. The problem statement should say what the system must do, for whom, and in what environment. Listing candidate solutions, including simpler non-AI options, prevents the team from committing too early to the wrong approach. Blurb analysis widens the lens beyond model building and asks whether the idea makes sense from several practical angles. MVP thinking keeps the scope small enough to stay useful once hardware, power, latency, connectivity, and maintenance enter the picture. Feasibility work asks whether the idea can survive reality. Moral feasibility, business feasibility, dataset feasibility, and technological feasibility each answer a different question about responsible use, value, data availability, and performance under constraints. The packet also needs the project goals and the standards for success. In Edge AI, those goals are often practical targets like faster detection, fewer false alarms, or operation within a power and memory limit, and the time and resource boundaries need to be stated plainly. Design planning turns the chosen idea into something buildable. It records the flow of data and decisions, the hardware and software choices, and the support plan for maintenance, updates, fallback behavior, and ownership after launch. Freshline Inspector shows why the packet matters in a production setting. Because a simple sounding inspection idea becomes full of concrete decisions once the line, the cameras, and the response process are examined. A defect detector has to define what counts as a defect, how fast it must respond, whether the camera view is sufficient, and what happens when a model is uncertain. Those questions turn the concept into something that can actually be reviewed. The problem description, solution comparison, feasibility notes, application flow, and architecture documents each handle one part of the decision. Together, they show whether the system is feasible, appropriately scoped, and ready for deployment. A lighter device like Riverwatch Node still needs the same basic set of documents. The difference is not whether the work is documented, but how much detail the situation demands. These documents are created early, but they should keep changing as the team learns more. Revision is part of the method because better information should sharpen the design rather than leave it frozen. A feasibility note can be corrected, a goal can be sharpened, and a hardware choice can be replaced when the facts change. That flexibility is a strength, not a failure. When the current idea is compared with the recorded one, scope drift stops being silent. The team can see what improved, what broke, and why one design choice fits the problem better than another. Teams that document scope, feasibility, constraints, and rationale are easier to review and easier to coordinate across disciplines. Good documentation removes confusion before it becomes expensive. If the package shows the idea cannot work, the team should narrow the scope, redesign the approach, or stop. If the packet is coherent, development can begin with far less guesswork and much stronger shared understanding. The standard is not just having ideas. It is producing the documents that demonstrate a credible path to a buildable system. That is what marks early edge AI design as ready for engineering.